One or more bolide impacts are hypothesized to have triggered the Younger Dryas cooling at approximately 12.9 Ka. Everybody knows that's 1,000 years ago. Per 1,000 K is 1,000, A is annum, right? In support of this hypothesis, varying peak abundances of magnetic grains with iridium and magnetic microspherules have been reported at the Younger Dryas boundary. The Younger Dryas boundary site in Pennsylvania is remarkable in yielding 2 to 5 millimeter diameter spherules containing minerals such as swacite, which is an iron nickel silicide, it's called. If you would, while I'm reading this, Kyle, if you would look up the word SU, actually it's probably Susite after Sus, SUESSITE, and we'll come back to that, and you can give us the definition. But the significant thing is that swacite or Susite forms at temperatures in excess of 2,000 degrees centigrade.
Yes, this is from Wikipedia. I think it might be Susite.
I think it is Susite
because it was named after
Hans Seuss.
That's right, Dr. Seuss.
Dr. Seuss.
There we go. Susite is a rare iron silicide mineral with chemical formula Fe3Si. The mineral was named after Professor Hans E. Seuss. It was discovered in 1982, etc.
Okay, so there we go. So here's the important thing about it. It forms at temperatures in excess of 2,000 degrees centigrade. That's pretty damn hot. Gross texture, mineralogy, and age of the spherules appears consistent with their formation as ejecta. Ejecta, in other words, thrown out, ejected from an impact 12.9 thousand years ago. The osmium 187, osmium 188 ratios of the spherules are often low, but osmium in these objects is terrestrially derived. Now that's interesting. In other words, our ratio of the two types of osmium isotopes in terrestrial rocks. So what this is showing is that in some of these rocks that were apparently vaporized, there is crustal material. So in other words, there was an event that happened that was in excess of 2,000 degrees centigrade. Now, here's interesting. The rare earth element patterns and the strontium and neodymium or neodymium isotopes of the spherules, because of their, in other words, looking very closely at the chemical composition and looking at the patterns of these rare earth elements that are preserved in these microspherules that were formed in excess of 2,000 degrees centigrade, right? They match the same signature of these other rocks, and their source can be identified by looking at those patterns and matching where were their crustal rocks potentially derived from. See, so that's the question. Because of the fact that the osmium at 187, 188 ratio is the same as what you find in a crustal rock, that tells you that a lot of these spherules that formed out of this vapor cloud were derived from terrestrial rock, right? So now we have to conceptualize an event that is going to melt enough terrestrial rock, presumably mix it with the melting of the impactor itself, dose the landscape with these microspherules, billions, trillions of them, okay? Now what we're doing is we're going to match those to their source rock and look for rocks that have that same pattern, that same signature, right? So that they say they're the rare earth element patterns and the strontium and neodymium, I'm not sure, neodymium, I think, isotopes of the spherules indicate that their source lies in the 1.5 billion-year-old Quebecia terrain in the Grenville province of northeastern North America. Got that? The terrain is called the Quebecia, so it's obviously related to the name of the province in Canada, which is Quebec, right? The geological term is the Grenville province, the Grenville province, which is this collection of these rocks that have been brought together through tectonic processes. So then the significance of this study, as it says here, is that it ties the spherules recovered in Pennsylvania and New Jersey to an impact in Quebec about 12,900 years ago at the onset of the Younger Dryas. Our discovery resulted from an exhaustive search that examined the question of whether there is any evidence of extraterrestrial platinum group metals present in the bulk sediments, magnetic grains, and spherules recovered from the Younger Dryas boundary. We find that the spherules are likely quenched silicate melts produced following the impact at the Younger Dryas boundary. The source of the spherules osmium, however, is likely terrestrial and not meteorite derived. That's interesting. So now we have this mix of this stuff, and part of it is derived directly from the crust itself.
That's the ejecta. You have an impact and things get blasted off out into the perimeter of where the impact is. And so they're finding it however many hundreds of miles away in Pennsylvania and New Jersey.
Yes. Thank you. That's exactly concisely it. Yes. They're finding these microspherules at these sites in New Jersey, these Clovis sites in Melrose, Pennsylvania, and in New Jersey. And we know that it was an extremely energetic event because and so these microspherules, again, they have this quenching pattern. So something that's rapidly melted, rapidly cooled, right? That's the scenario here. And then you got trillions of these things just, falling back to Earth. Very small, microscopic. Very much like we find with the Tunguska event, which again, we've got coming up much more in-depth examination of the Tunguska event because it's one of the critically important cosmic teaching events, certainly one of the most important of the 20th century. And that's why I want to dwell on it a bit.
Also, 2,000 degrees Celsius is 3,600 degrees Fahrenheit. I looked that up.
Okay.
3632.
3632. So in other words, pretty damn hot.
Also interesting about, those microspherules have terrestrial origin. So that tells you that, like they're saying, there's a bombardment event where some of them are exploding in the air, but some of them definitely hit the ground.
Yeah.
Right. Otherwise,
I think that's what it's telling us. And I think that's one of the reasons why the evidence is so diverse. And that has been one of the objects of criticism, is because some of the studies seem to suggest it might be carbonaceous. Other studies suggested it might be iron in nature. That was what Pateev, God, I wish I knew how to say his name, was speculating, left the signature of platinum in the Greenland ice. Okay, look what I got up here. Okay, so this is the Grenville province, which is this collection of these different exotic terrains that have come from many sources that have been pushed together and kind of welded together. And there are a lot of different rock types, right? So each one of these rocks types of rock, each of these different lithologies are going to have their own unique isotopic signature. So the isotopic signature in the microspherules found in Pennsylvania match the rocks of Quebecia, which you see right here in the center of the screen, right? If we go back, let's see here. The rare earth element patterns of strontium and neodymium isotopes of the spherules indicate that their source lies in the 1.5 billion year old Quebecia terrain. To date, 184 confirmed impact structures have been identified around the world. Crater structure, shock metamorphism, and a meteoritic contribution are important markers used to confirm an impact structure. However, a visible crater, breccias, and high-pressure modified minerals remain unreported for the YDB horizon, with the exception of possibly shock-synthesized hexagonal nanodiamonds, an observation disputed by Dalton and co-workers. The proponents of the YD impact hypothesis have pointed out, however, the lack of traditional impact markers in a number of widely accepted impact events, such as the Australasian tektites, the Libyan desert glass, which we discussed, the Tunguska event, all suggested to have resulted from non-crater producing airbursts. Thus, a lack of traditional markers at the YDB may possibly be the result of one or more impactors exploding in the atmosphere or striking the Laurentide ice sheet. Aha! Now, here's an idea proposed in 2013 that we have been advocating for at least since the 1980s. That was the objective of Brad and mine's first excursions in 98 and 99 to look for evidence of meltwater floods produced by impacts onto the ice sheet. And I think Brad will confirm that I'm not making that up. So
we were doing it in 98, 99 for sure.
We were. Okay, so now here we go. Here's that Quebecia terrain. Notice in here, this where I'm coming down with my my mouse, that's the St. Lawrence Seaway, right? Okay, let's go to the next one. Now you see Quebecia superimposed right on the land, right? Here comes the St. Lawrence Seaway. Quebecia is located in central Quebec near Bayou Comeau and Forestville. It is bordered to the south by the St. Lawrence River. Quebecia is an accreted arc, meaning accreted. Its pieces come together in calc-alkaline composition. You don't need to worry about what that is necessarily, but that's a very unique terrain. And so it has the proper signature to have been the source of the microspherules found in Pennsylvania. Got that? So now we look at Quebecia and we zoom right in. Right here, where I've got the red dot, which is right about under the U of Quebecia, this is what we find. Lac St-Jean, right? The Saguenay River flowing out into the St. Lawrence. We find this basin. We see certain geomorphic similarities, I would say, or parallels to Lake Nipigon. Do we not?
Oh, yeah.
We've got a basin occupied by a lake. We've got what appears to be an outflow channel. At Nipigon, clearly, there's evidence of catastrophic outflow. How about here? I believe that Brothers of Serpent might have a few images we can look at. There we go. Now, those cliffs have all the earmarks of having been produced by catastrophic flows. Look at the cliff on the right. It's sheared off. It's a shear face. And you can actually see, very similar to some of the cliffs that you see in Eddy Narrows along the Clark Fork. You can follow up and you'll see scoured rock up to a certain level. And then above that level and below that level, you only have very scant trees. There's very little topsoil. Above that level, you have trees growing because there is more topsoil. If you look on this cliff right here, you kind of see the same thing. Now, this is now forested all the way down. This actually might be a mass wasting event here that's forested. We don't know. It's going to require field investigation. But sheer cliffs are certainly one of the diagnostics for catastrophic flows. Problem is here, if we can see the bottom of the fjord and look at the texture of the rock, yeah, look at this. See, this is a sheared cliff. This is a vertical cliff. This is exactly what you see in acknowledged mega flood created landscapes. For example, Grand Coulee, where you have sheer cliffs like this that are 800-900 feet high, right? Moses Coulee, another example of that. Cliffs along the Clark Fork River, where you can see the bare rock sheared off up to the high water mark. Yeah, look at this. See, look at the texture of this rock.
Wow.
Yeah, it's sharp and has been scoured. Clearly.
Yes, exactly. Once you begin to recognize this, and like Brad and I have spent countless hours in the field looking at this stuff, kinds of things that is acknowledged the result of catastrophic megafloods. And once you begin to see it, it becomes more and more obvious, because For one thing, in these floods, the shear forces are so intense, right, that they just pluck and pull. Now, in a lot of the coulees of the Channel Scablands flood, it's a basalt bedrock, which tends to pluck apart on the cleavage plains, right? Because you have most of it is columnar basalt, but there's also Hackley basalt. But the point is that whether columns or whether Hackley, it's gonna plug and it's gonna leave a very distinct texture on the surface of the rock. Other types of rock will degrade and erode differently. If it's a limestone type rock, it tends to form the rocks tend to get dissolved very quickly because once they're carried in the floodwaters, they're quickly ground up, and limestone tends to be dissolvable in acidic waters. So
yeah, and it's also soft.
And it's
pretty
soft, right,
rock,
right.
yeah.
And again, like if you have a limestone, you could have the same thing. It can disaggregate and actually produce huge sandbars. You take a big chunk of sandstone and you carry it in a swift, catastrophic, highly energetic torrential flood for 50 or 100 miles. By the time you get 100 miles down, it's been reduced to a pile of sand. You see. So it affects, you have to look at different rocks differently. But and I have not looked into the lithology of this area in depth yet. But that, of course, would be part of the pre-field work, where you would go for the studies, try to access, there's probably been core samples off the bottom of the fjord. I'd like to know really what's laying on the bottom of that fjord. What is are there large scale rocks? Is it really what is it? What is it? What's on the bottom?
How deep and sharp is it cut?
Yeah. Are there drowned cataracts? That kind of thing. Yeah.
Yeah.
Here we go. This colored digital elevation model really shows the basin, and you can see the trough that's occupied by the fjord. And it's since we don't know now I gave you the 50 feet above the water level of the fjord. How deep is the fjord? Because really that's the depth of the chasm there. Now the number giving the cliffs. So I gave you the differential between the surface water of the fjord and the top of the adjacent cliffs. How deep is the fjord? In other words, when you look at this channel right here that I'm running my mouse along, how deep is that channel? But yeah, that's a pretty impressive geomorphic feature right there. And if it's consistent with Nipigon, and what I'm now strongly suspecting is that you had a melting event that was centered over the basin, and you had a large catastrophic outrush of water this way into the St. Lawrence Seaway. Now, one of the things one might do is study what kind of drowned deposits are off the mouth of the Saguenay River on the bottom of the St. Lawrence here. And that would tell you something. So
also, if there's studies on the depth of the sediments at the bottom of the fjord, if it's like the Okanagan Valley or the Finger Lakes, even, they were scoured out and gouged and then filled in with all kinds of, hundreds and hundreds of feet of sediment. So the bottom of the lake is not necessarily the bottom of the channel.
Exactly. And that also holds true for the lake itself, because now we're talking about 200 and some feet of depth, but that is to the sediment layer, not to bedrock.
Right. That's what I was saying too, because it's been wet, there's going to be all kinds of sediment in the bottom.
Yeah. Now,
also the fjord has an average.
Oh, sorry. What?
Sorry. The fjord has an average depth of 210 meters, which is 690 feet.
Wow.
With the deepest point being 270 or 890 feet.
890 feet. Now, interestingly, because that puts it, 900 feet is like the depth of Grand Coulee. So, yeah, I'm thinking now more and more that I'm looking at this, I would say that this would be a candidate impact site right here. And so if you look at this, the terrain, I'll stop this share. If we look at the terrain of the Quebecia, which is the source rock for the microspherules, right? Think about it. We got microspherules in Pennsylvania. Where did they come from? They came from this Quebecia terrain, which is almost wholly occupied by this feature we're just looking at, right? And we find a basin. So the microspherules are consistent with an impactor and terrestrial rocks that presumably, if this was an impact site, would have been excavated in the process of releasing all of this tremendous heat and energy. So the microspherules
really cool.
are consistent with there being something enough to melt and presumably excavate this bedrock at this site right here. So I don't know. I would say it's looking darn suspicious to me. And like Brad said, if you had a layer of ice over this that could be, thousands of feet thick, that is going to create a whole different kind of an after effect than, say, a direct impact into an unglaciated land surface. And just like with an impact into an ocean, there's a transient crater produced and the water is forced outward, right? But then it rushes back in. It collapses back into the crater, which you don't have that effect with a land impact. Now you'll have breccia and material, the fallback breccia that falls into the crater, absolutely. And you'll probably have some seismic repercussions that will cause slumping, and you do find that slumping within the rim of the crater back into the crater itself. But obviously you're not going to have this huge resurge wave, as it's called, that rushes back into the crater and carries a whole lot of sediment with it when it does it, you see. So when that resurge wave rushes in now, it's filling up the basin and leaving behind this thick layer of sediment. So what we need is core samples from the bottom of this lake, like you were saying, Kyle, core samples, and Brad, along the river itself to see what's on. And there's probably been some kind of bathymetric surveys that have looked at what's going on down there. I haven't looked at any of those yet, but see, that would be where one would start, I think, to try to find out, first of all, to establish that, yes, there had to have been some type of an energetic event, obviously, to cause this melting and the catastrophic outrush of water. Now, when we go to Nipigon, the idea there is that this was the catastrophic draining of Lake Agassiz. Well, there's reasons, I think, to consider that maybe that's not what it was. And we're going to get into that. I've got a whole program I'm putting together just around this Nipigon, because that's still one of the areas we need to get out into the field and research. But now maybe we could figure something, we're going to the Scablands next fall, so I don't know when we'd get up there. But hey, once we get rolling here and we have the resources, we're going to be doing regular excursions to be documenting this stuff on a higher level, on a level that it really needs, the kind of attention it really needs to be getting. Because there needs this. What we've got now is a group of scientists that are working on this part-time, but it needs a much higher priority than that. This is not a part-time scientific question. This of mere academic interest, and that's kind of one of the whole points I've been trying to push here through this series that we're talking about here, is that all of this information has tremendous relevance for our own future, because we are going to be laying out week by week the evidence that this planet has been pummeled far more frequently than anybody had even realized, even now. And, that's a pretty bold statement to make, but I'm willing to say, let's back it up with the evidence. I mean, if we start looking at the evidence, we're just left with the conclusion, the unavoidable conclusion that, sometimes these tremendous catastrophes happen. There can be a number of causes, but probably the most frequent one is extraterrestrial in origin. And we find the signatures of these events, both the fingerprints and the footprints, as we talked about, all over the planet through all times that we look at. And there's nothing to conclude that such processes are somehow non-operational at present.